Welcome students. Today we will study the first chapter from paper 1, circular motion. In general, motion of a body is change in its position or part of the body with respect to an observer. Circular motion is motion of a body along the circumference of a circle. For example, motion of the earth round the sun or motion of the electrons round the nucleus are the examples of circular motion. In the figure, a body is shown moving along a circular path of center O and radius R. It is moving in anti-clockwise direction. A, B, C are the different positions of the body. Anytime the linear velocity of the body is directed tangential to the circular path or perpendicular to the radius. Suppose the body starts from A and in time t it moves to B. If O is the center of the circular path, then it can be considered as the origin of the coordinate system. Then OA is the position vector of the body when it is at A. Similarly, OB is the position vector of the body when it is at B. Hence, vector OA, vector OB and vector OC represent position vector of the bodies when it is at A, B and C respectively. These position vectors are also called radius vector. When the body moves from A to B, it inscribes arc S in time t and subtends angle theta at O. Then the angle subtended by the position vector or the radius vector in the given time at the center of the circular path or at the origin of the coordinate system is called angular displacement. So theta is the angular displacement in time t. But theta is not called a true angular displacement because an angular displacement ought to be a vector quantity. Theta is not a true vector quantity because it does not obey all the laws of vector. Hence, consider further very small or infinitesimal displacement delta theta from B to C in very small time delta t. This very small angular displacement delta theta obeys all the laws of vector, hence it is true angular displacement. Hence, throughout the chapter, we will consider delta theta as the angular displacement. It is measured in radian. Suppose the body moves from A to B, subtending angle theta in time t, then as per the definition of velocity, the average angular velocity will be angular displacement theta upon time t. Hence, an average angular velocity, which is denoted by omega average, is given as theta upon t. Its unit is radian per second. But as theta is not a true vector quantity and we consider delta theta as the true vector quantity or true angular displacement, we always find instantaneous angular velocity instead of average angular velocity. Consider that very small or infinitesimal displacement delta theta from B to C be occurring in time delta t. Then the instantaneous angular velocity omega is given as limit delta t tending to 0 delta theta upon delta t. By definition, this is the time derivative of theta, so it is denoted as d theta by dt. The unit of angular velocity is radian per second. When the angular velocity is not changing, or when the magnitude of linear velocity v is not changing, then the body is said to be moving with uniform circular motion. So uniform circular motion is defined as circular motion or motion of a body along the circumference of a circle with constant linear speed or constant angular velocity. It is found that in UCM, the instantaneous angular velocity is magnitude wise same as average angular velocity. When the body is not in UCM, that is, when the angular velocity of the body is either increasing or decreasing, then the body possesses what is called angular acceleration. So, if angular velocity of a body changes from omega 1 to omega 2 in time t, then average angular acceleration alpha is given as omega 2 minus omega 1 upon t. But this is the angular acceleration over a large period. For calculating the instantaneous angular acceleration, we have to limit the change in the angular velocity to 0, or we have to find out the limiting value of change in the angular velocity, or we have to find out the change in the angular velocity for very small time, which is almost tending to 0. Hence, like instantaneous angular velocity, angular acceleration alpha also can be given as limit delta t tending to 0, delta omega upon delta t, and by definition it will be the time derivative of angular velocity omega. So angular acceleration alpha is given as d omega by dt. Its unit is radian per second square. Then different linear quantities are related to the quantities in circular motion like this. There is a relation between linear velocity v, angular velocity omega, and position vector r or radius r. It is given as v is equal to r omega. Vectorally, it is the cross product of omega and r. Similarly, when the body is not in UCM, its linear velocity changes. Even though it is in UCM, though the magnitude of velocity, that is speed, is not changing or remaining constant, as the direction of linear velocity changes, there is always an acceleration. This acceleration is called tangential acceleration. This tangential acceleration at is given as the product of r, that is position vector or radius, and alpha, which is the angular acceleration. Hence, at is given as r into alpha. Up till now, we have studied many vector quantities such as angular displacement, angular velocity, angular acceleration, linear velocity, tangential acceleration, etc. The directions of all these quantities can be obtained with what is known as right hand rule. Referring to the second figure, in which a body is moving in anti-clockwise sense about the axis passing through O. The body is moving in the horizontal plane and the axis of rotation is vertical, that is perpendicular to the plane in which the body is moving. In such case, the law gives the direction of all the vector quantities. The law states that imagine your right hand with the thumb outstretched and the fingers curled round the thumb. If you imagine the axis to be held in your right hand and the curled fingers indicating the direction or the sense of motion, then the thumb indicates the direction of angular displacement, angular velocity, angular acceleration, and rest of the directions also can be obtained. So in the figure, if we consider the thumb to be in the direction of axis or along the axis and the fingers in anti-clockwise sense, then the thumb will be in the upward direction. So the thumb will indicate the direction of vector delta theta, vector omega, and vector alpha. One more direction is also shown for vector alpha. It is below the axis, or rather it is below the plane of the motion. Why these two directions are there for alpha? All of you know that whenever velocity increases, the acceleration is positive, or whenever velocity increases, the direction of acceleration is same as the direction of velocity. Hence, as omega increases, the alpha will be positive, or alpha will have the same direction as that of omega, and hence 1 alpha is shown below omega and it is in the upward direction. The direction of alpha is upward when omega is increasing. When velocity decreases, a negative acceleration or deceleration or retardation is produced, or when the magnitude of velocity decreases, the direction of acceleration is exactly opposite to the direction of velocity. Hence, one more direction of alpha is shown, which is in the downward direction, and that direction of alpha should be considered when omega is decreasing. Hence, according to whether omega is increasing or decreasing, alpha will have upward or downward direction. Upward for omega increasing, downward for omega decreasing. Consider the body to be at position P. It is rotating in anti-clockwise sense, so the direction of linear velocity is tangential to the circular path, or it is perpendicular to the radius OP. The tangential acceleration AT is also directed along the direction of V, and that's why in that vector two directions, direction of linear velocity V and direction of tangential acceleration AT are shown. Then when the body is in UCM or non-UCM, one acceleration always acts on the body, or one acceleration is always produced in the body, which is known as centripetal acceleration. It is always along the radius and it is always directed towards the center of the path. Its value is V omega or R omega square or V square upon R. This acceleration is always directed towards the center, and that's why it is known as centripetal acceleration. It is always along the radius, and that's why it is also called radial acceleration. For a body in UCM, there is no change in omega or angular velocity. Hence, there is no angular acceleration. Hence, there is no tangential acceleration. But as the velocity is changing in direction, there is always a centripetal acceleration. When the body is not in UCM, then its angular velocity omega may change. Then it will have angular acceleration alpha. Then it will have tangential acceleration AT. And in such case, the body can have 4 accelerations. Alpha is shown along the axis up in the upward direction. Tangential acceleration is shown in the direction of linear velocity V. Centripetal acceleration is shown along the radius towards the center, And now last two accelerations, that is tangential acceleration and centripetal acceleration, both are in the plane of motion, that is both are in the horizontal plane, and look at the directions, both are acting on the particle at P. Hence, their resultant can be drawn, and that resultant is denoted by A. So A is the fourth acceleration which a body possesses when it is in non-UCM. And that resultant acceleration A is the vector sum of vector AT and vector AC, that is tangential acceleration and centripetal acceleration. Hence, vectorally it is given as vector A is equal to vector AT plus vector AC, and magnitude wise it is given as A is equal to under root AT square plus AC square. Directions of all these accelerations are also shown in that diagram. Whenever there is an acceleration, obviously there will be a force acting on the body, because acceleration is the result and force is the cause. As a body in UCM is always acted upon by centripetal acceleration, there must be a force acting on the body which is causing this acceleration. This force is called centripetal force, denoted by FCP. Now, the force has the same direction as that of the acceleration, or vice versa. The acceleration has the same direction as that of the force. If the centripetal acceleration is along the radius towards the center, the force, centripetal force, which is causing that acceleration is also along the radius towards the center. So, FCP, centripetal force, is also shown in the figure. Now, whether the body is in UCM or non-UCM, it is always acted upon by an acceleration. So it is always in an accelerated frame of reference or non-inertial frame of reference. For a body in non-inertial frame of reference, to apply Newton's law, we have to consider a pseudo force which is equal in magnitude of that of the real force, but acting in a direction opposite to the real force. In circular motion, such kind of real force is the centripetal force, and to imagine the other force, the pseudo force, we consider another force acting which is of same magnitude and acting in the opposite direction, that is along the radius and away from the center. Such a force is called centrifugal force. This force also has same magnitude but the opposite direction. Now, we already got the magnitude of centripetal acceleration as V omega r omega square, or V square upon r. If we multiply this acceleration by mass, we will get the force. Hence, the formulae for centripetal force are mv omega or mr omega square or mv square upon r. As it is a force, its unit is Newton. Similarly, the centrifugal force, which is magnitude wise same but the direction wise opposite, is also given by mv omega or mr omega square or mv square upon r, and its unit is also Newton. So this is how different forces are acting on a body in circular motion. Then, on a curved road, whenever any vehicle is taking a turn, then centripetal force is necessary for the motion. In case of a plain road or in case of a horizontal road, this centripetal force is provided by the friction between the tires and the road. If a vehicle of mass m is moving on a curve of radius r with velocity v, then the centrifugal force acting on it is mv square upon r, and the centripetal force necessary for the circular motion is mg mu, or the force of kinetic friction. When these two forces will be equal, then the vehicle can safely take the turn. and that's why the safe speed on unbanked road is given by the formula V is equal to under root mu rg, where mu is the coefficient of friction between tires and the road, r is the radius of curvature of the path, and g is the acceleration due to gravity. So by increasing r or mu, we can increase the safe speed. If the centrifugal force becomes more than centripetal force, the vehicle is likely to be thrown off tangentially. Now, this method of increasing the safe speed by increasing the coefficient of friction is not an advisable method, because in order to increase the coefficient of friction, if you make the road rough, then coefficient of friction will definitely increase, but that rough road will cause wear and tear of the tires, and that coefficient of friction mu may not remain constant. Due to overuse or due to water or mud or oil on the surface of the road, mu may decrease and the safe speed limit will also decrease. Hence, banking of roads is an advisable method. In banking of roads, the road surface is tilted, or the road surface on a curve is made such that the outer edge of the road is slightly elevated with respect to the inner edge, so that the road bed makes some angle with the horizontal. The angle made by the road bed with the horizontal is known as angle of banking, and in that case the safe speed is given by the formula V is equal to under root rg tan theta, where r is the radius of the curved path and theta is the angle of banking. Now in this formula, there is no risk in increasing the safe speed by increasing the angle of banking. So as the angle of banking increases, the safe speed can be increased. In both the formulae, there is no mention of mass of the vehicle, so both the formulae are independent of mass of the vehicle. So banking of roads is a advisable, or banking of roads is a preferred method to increase the safe speed on a curved path. Up till now we have considered the circular motion only in horizontal plane. Now let us consider the vertical circular motion, that is circular motion in vertical plane. It is a bit different from the horizontal circular motion, because in horizontal circular motion the velocity of the body, that is the linear speed of the body, can be kept easily constant. In case of vertical circular motion, when body goes up, the acceleration due to gravity retards the motion, and when the body comes down, the acceleration due to gravity helps the motion. This is the reason why when the body is going up, its velocity goes on decreasing. When the body comes down, its velocity goes on increasing. And that's why analysis of vertical circular motion is bit different. The figure shows vertical circular motion of a body in anti-clockwise sense. The center of the circular path is O and the radius is R. So consider it to be a heavy body suspended with a thread R meter long to the point O, or it is rotated about point O. For that body to complete the vertical circle successfully, the velocity at the top of the motion or at the top of the circular path should be under root rg. If velocity of the body at the top of the path is less than that, then at the top the body will fall vertically down. For that, the velocity at the bottom should be under root 5 rg. So in general, you can say for a vertical circular motion or for a successful vertical circular motion, the velocity at the bottom should be under root 5 rg, so that it will reduce to under root rg at the top and the body will be able to complete the vertical circle. The velocity in between, that is velocity when the string becomes horizontal, is under root 3 rg. Even though the velocity of the body in vertical circular motion is all the time changing, the energy of the body remains constant, because while going up the velocity is decreasing, so the kinetic energy decreases. While coming down the velocity is increasing, so the kinetic energy is increasing. But while going up, the height of the body with respect to the position at the bottom increases, and that increases the potential energy of the body. While coming down, the kinetic energy increases, and as the height of the body with respect to the bottom position decreases, its potential energy decreases. And sum of these two energies, that is total energy of the body, remains constant. Hence, while going up, the kinetic energy decreases and potential energy increases by the same amount. While coming down, the potential energy decreases and kinetic energy increases by the same amount. But the total energy of the body remains constant. That total energy is found to be 5 by 2 mgr. In case of vertical circular motion, at any position, different forces are acting on the body. Two main forces out of that are the weight of the body mg, which is acting vertically downwards, and tension in the string T. Now that tension in the string at any position of the body is given as T is equal to mv square upon r plus mg cos theta, where theta is the angle made by the string with the vertical, m is the mass of the body, v is the velocity of the body at that time, and r is the radius of curvature or radius of the curved path or length of the string. By putting different values of theta in this formula, we get maximum tension, which is at the bottom when theta is 0, as mv square upon r plus mg. When the body is at the top, theta is 180, cos theta is minus 1, so tension is mv square upon r minus mg. This is the maximum and minimum tensions in the string due to the vertical motion, respectively at the bottom and at the top position. For any other position, you have to use the general formula T is equal to mv square upon r plus mg cos theta. This is how the vertical circular motion also can be analyzed. In vertical circular motion, the linear velocity can be forcefully kept constant. But for that, you have to increase the velocity of the body when the body is moving up, and you have to retard the motion when it is coming down. But it can be kept constant. And when the body is moving in vertical plane, its linear velocity is in the vertical plane, but the angular displacement, angular velocity, angular acceleration, all these quantities will be perpendicular to the vertical plane, that is, they are in the horizontal direction.